glad to see you made it back. As usual, let me get started with the ink here so I can annotate. We're in good shape. Do a little test here, and we're ready to go. We're going to talk about some applications today, and we're sticking with linear equations. That means the highest exponent is a 1. The only exponent of x's, y's, z's is a 1. So, most of you probably have a difficulty with word problems. We're going to try to solve some of that for you. There we go. And here are some steps. I would suggest you write them down and also annotate them as we go along to put them in your own words and maybe to amplify them, make them even more informative. So read the problem. That seems obvious, but when I work a word problem, I probably read it through 2 or 3 times. One to get an idea of what's going on, another one to pick out some details and find out what I'm looking for, and then I'll go back maybe a 3rd time and I'll pick out the individual pieces. What is the speed? What is this? What is that? And write them down all in one box so I don't have to keep reading it over and over again. Step 2. Now on this one, actually, as you'll find out, I changed this into 2 parts. Because assigning a variable actually, I think, represents 2 different steps. And you'll see what I'm talking about. But one thing to keep in mind is when you decide you're going to jump into writing an equation, if you haven't written down what x is going to represent, you're making a mistake. So please, x equals what? Speed of Joe, for example. And you might even put in that's in miles per hour. You can't have too much information in front of you so that when you want to reference it, it's right there. And you don't have to go back and read the problem again, most likely, until the very end. Write an equation with those variables and what the problem actually says. Number 4, solve the equation, obviously. If you've got a good equation, you need the good equation, or solving the equation won't help. Step 5, write down what the answer is to the problem. Remember, the question was in words. Your answer should be in words. If you're looking for how far Joe is from St. Louis, write down, Joe is 17 miles from St. Louis. Don't just say 17 miles. State the answer. That's supposed to be in words. Number 6, check the answer. So, check your answer, the written word, against the original problem. Do they match up? When you go through the original problem with the numbers that you found, does it actually make sense? Do you end up with something like 16 equals 16, for example? You'll see what we mean. So here's an example we can use, a word problem, and we're talking about a square. So first of all, think to yourself, okay, square. So you might actually draw a little bit while you're going through this. And it says the length of each side of the square is increased. So you've got one square and you've got a bigger square because it's increased in size. It says the perimeter of the new square is 40 centimeters more. So you're talking about perimeter. So that's the distance around the square. But the one we're talking about here is the new square. So if you start here and you go all the way around the square, how far do you have to go? And this says if you go around the new square, it takes you 40 centimeters more to get the whole way around. And then find the dimensions of the original square. So your answer would sound something like the original square measures blank centimeters by blank centimeters. Okay, ready to go? Let's give it a shot. So we've read the problem, or pause this video, read the problem, make some notes perhaps. We want to find the length of the original square, so that might be what we want to represent by x. That would be the easiest. 2a, notice I put in the two parts. 2a, assign a variable. Because the length of the original square is to be found, let the variable represent this length, x, y, s, whatever you want to. So there's your x's, and there's your picture. Pictures really help, so make sure you draw a picture. No matter how poor an artist you might be, you're probably better than I am, but I still draw pictures because they help me. And the length of the side of the new square is 3 centimeters more. What does that look like? Well, there's a new square. Notice the original square over here had a side x. That's what we're looking for. The new square over here, new square. You could even put original square here. You can't write too much down. It says the side is increased by 3. Increase means 3 more. In other words, if this is a 17 over here, then the new one will be 20. So x for the original side, x plus 3 for the new square side. Next, assign a variable expression. Write an expression for the perimeter of the new square. The perimeter is 4 times the length of a side. You might want to put this in your permanent notes. Perimeter for a square equals 4 times the length of one of the sides. Put that away. Since the new square, the new one that is, has this for its side, we're going to multiply that by 4 because there are 4 sides, and that'll give us the perimeter of the new square. Step 3, write an equation. Translate that into equivalent algebraic expression. This is exactly what I do, especially when I'm working it on the board to show you some other problems. The new perimeter is, well, is going to translate to equals. The new perimeter, well, we just found an expression for that, 4 times the side, which is x plus 3, and it says is what? 40 more than. Well, I might write this a little bit different, because if you were calculating this part over here, you would probably start with this length of the side. Let's use s for a moment. Start with, well, no, let's use the x. You start with the x, and twice that would be 2x. 40 more than that, 40. But if you see it as 40 plus 2x, that's fine. We're still working with the same expression, just a different look. Step number 4, the part we've been waiting for is solve the equation. Get all the x's on one side, all the numbers on the other side, divide by the coefficient of x. The coefficient of x is 2, divide both sides by 2, and there's your 14. Remember what x represents? Well, if at the beginning you wrote down x equals what? Well, x represents the length of the original square. So that's what we've got. And as you made a note of, it'll be in centimeters. So what's the answer? Each side of the original square measures 14 centimeters. Notice that it's a complete sentence. A complete sentence. and it tells exactly what we were looking for. It's about the original square, how long each side is, and how long that each side is, 14 centimeters. Number 6, check. Go back to the words of the original problem, and using that 14, make sure that everything that was there is satisfied. So the length of the side of the new square, since the original was 14, the new square would have a side of 17 centimeters. And the perimeter, 4 times that, 68 centimeters. Twice the length of the original square would be 2 times 14, that's 28. Add 40 to that, 68. It checks. Good job. Another hint, if you've got a motion problem, like Joe is traveling to St. Louis, maybe he's going from Pittsburgh to St. Louis, and you've got, usually in rate problems, you've got distance, rate, and time. Here's another formula you want to keep in your back pocket. Distance equals rate times time. So make a note, D equals distance, R represents the rate, that'd be like miles per hour or feet per second or meters per second, whatever, and T will be the time. And that time, depending on the actual problem, might be in seconds, minutes, hours, even days or years. The two over here are really the same as what we've got here. This is the original. By just juggling this algebraically, we can get this formula and this formula. So don't bother knowing those. Make sure you know distance equals rate times time. Okay, let's try one of those. We've got Maria and Eduardo. They're traveling to a business conference. The trip takes 2 hours for Maria and 2.5 for Eduardo because he lives 40 miles farther away. Eduardo travels 5 miles per hour faster than Maria. I guess he's trying to make up for that difference. Find their average rates. In other words, speeds. Speeds and rates represent the same thing. It's not always miles per hour. It could be light bulbs per hour that you're making. It could be lots of different things. So their rates, their speeds. So first of all, read the problem. Go back if you need to, or pause it. We want to find Maria and Eduardo's average rates. Now here's a tip. This is what I use almost all the time, but depending on the problem, I might switch it up. Where's my, there we go. Okay. So we've got 2 things we're looking for, 2 different speeds. Tip. Let X or Y or Z, whatever it is, equal a smaller number. Now which one is going faster? Well, it says back here that Eduardo was traveling 5 miles per hour faster. So that Maria was going slower. So what we're going to do is let X be Maria's speed. Make that a little bit short. And then Eduardo's, go back and check. I'm not going to continue going back and forth. So this is what it looks like. And this is a good idea for you to use. Use a table like this. Organizes things. Notice that on the top we've got the rate, time, and distance. Not only that, but if you pay attention, it's rate times time equals distance. So you've actually got your formula up here, and you're going to follow that down here with the individual pieces that you get from the problem. So there's Maria's speed because she had the slower speed. It took her 2 hours, so you fill those in. Well, real fast, you can figure out what the distance is. It's not given, so multiply those two together. 2x is how far Maria goes. Eduardo, a little bit faster. It takes him 2.5 hours because he was farther away. Rate times time. There's your distance for Eduardo. Time to write an equation. There's Eduardo's distance. It's 40 more than Maria's. So this is Maria's distance right here. 40 more than that, you add 40. So there's your equation, and we're going to solve that equation. There's the equation again written. Use the distributive property to multiply through both of those sides. Combine similar terms. Divide by the coefficient of x, which is the 0.5. So you have 0.5 into that, 0.5 into that. You might want to use the calculator on that one just to make it a little bit easier. But you know how to use your calculator, so you'll be a whiz at this. Step 5. We've got what we need, pretty much. The rate of travel is 55. That was x. And it's 55 miles per hour for Maria. And Eduardo is 5 more than that. So he went 60 miles per hour. Notice that what we've got for an answer, this is the answer. 55 is not the answer. The answer is Maria's rate of travel is 55 miles per hour, and Eduardo's rate is 55 plus 5, because he's going faster, or 60 miles per hour. There's your answer. Last of all, the diagram shows that the conditions are satisfied. So, Maria, do that calculation, put the 55 in for x for Maria. There's 110 miles that she goes. Put the 60 in for Eduardo's speed, and you find he went 150 miles. And what did it say? Eduardo went 40 miles more. Compare those. What's the difference? 40 miles. Now, we go to mixture problems. This doesn't have quite the visual appeal of the others. However, there's a way to work this. You're going to be working with the rate of concentration, or the amount of concentration. 50% sulfuric acid, or 6% milk, something like that. Or how much of that is sugar, for example. Notice the concentration of the final mixture must be between the two solutions. So if you have two containers, let's see, where's my mark here? Okay, so let's imagine we've got a container here with some liquid, and we're going to add to that some liquid from the second container. Now, if this container is a 5% solution and this one is a 10% solution, what we'll get by mixing those together, throw this in there, throw this in there, and what do we have? Well, because this one's 5% and this one's 10%, this one here is going to be between 5 and 10%, somewhere in the middle. Keep that in mind. That's going to be a big help to you. It might sound trivial, but when you're working the problem and looking at the answer, this is a big help. So here we've got a problem to work with. the chemist needs a 20% solution of alcohol. She has a 15% as well as a 30%. Notice that the final is between the other two. She's got a container that has a 15%. She's going to add it to something that has a 30% solution, and we're going to end up with one that's in the middle at 20% solution. Notice 15, 30, the 20 is between those two. Now, the question is, how many liters of the 15% solution should she add to the 3 liters of the 30 to get her 20% solution? So, read the problem. We want to know how many liters of the 15% alcohol solution we'll need. So that's what is going to be your X. Here's your X. There's your X. And that's how much of the 15% solution you need. Now it said in the problem that you're going to, and let's stick here, that what you need is to add it to 3 liters of the 30%. So 3 is already given, so you can put that in. You can put the liters in there if you want to, that's up to you. And these are the liters. This is the strength. This is almost like a distance, rate, time problem in a way, but it's different too. Now, one thing I might do here is that you've got the 15% and 30%. What's down here at the bottom is this adding together of these two. So I might put a double line here, just showing that we're going to take this, add this to it, and end up with the 20% solution. And as with distance, rate, and time, we take the concentration percent times the amount of the solution and multiply those together to find out how much alcohol. Now, this goes to something that is going to help you with these mixture problems. 15% of what? So I focus on, in this case, the pure alcohol. How much alcohol really is in that first container? Well, it's 15% of the X liters. Of means times, so 0.15 times X is how many liters of pure alcohol. In the second one, the same type of thing. You've got 30% of the 3 liters that we know. Of means multiply, so 0.30 times 3. And these are the two that you're adding together. And you're going to end up with, make sure that looks like a plus. You're going to end up with a 20% solution. And since you started with X and added 3 liters, that's how many liters you've got in the solution. Multiply that by 0.2, and that's how much alcohol is in your final container. So write the equation. So what we're doing is we're looking at pure alcohol. How much pure alcohol do we have in the first container? There we go. How much did we add of pure alcohol in the second container? And how much pure alcohol do we have in the final mixture? And then it's time to solve the equation. Use the distributive property on the right-hand side, multiplying by 0.2, and there you go. Get all the X's on one side, all the numbers on the other side. It doesn't matter whether you collect X's on the left or the right, that's up to you. Notice that the coefficient of X, our variable, is 0.05. So you're going to divide both sides by 0.05, 0.05, And there's your answer, x equals 6. What does x mean? It's how many liters of the 15% solution. So we're ready to state our answer. 6 liters of the 15% solution mixed with 3 liters, which we already knew, of the 30% solution, and that gives us 9 liters of the 20% solution. Again, one more time, notice that we've got this strength and we've got this strength. So when we mix them together, we end up with something between the two. Not exactly between the two. You can't take 15 and 30, add them together, divide by 2. It doesn't work that way. Don't even try that. Then we'll check it out. This amounts to how much alcohol is in the first container, the alcohol in the second container, and this is the alcohol in the mixture. And that's how much alcohol is in the final mixture. Now we'll take a look at some finance. We're going to look at some investment problems, and you're going to see maybe that they're a little bit similar. Well, notice before we had distance equals rate times time. Did you take a note of that and put it somewhere where you can find it? Maybe a special page or a special notebook that you keep formulas and ideas. Well, the formula we're going to be using here, this is the interest, this is how much money is invested, this is the annual rate, and this is the amount of time in years. Remember, time in years. Rate is the annual rate. Both of them are talking about years. That's important. Also, take note, P, although it represents the original amount, is represented by the word principal. Notice PAL. So here we've got something to play with. We have a painting for $410,000. Will you be buying that? P invests part of the money for 6 months at 2.65%, and the rest for a year at 2.91%. His broker tells him the two investments will give him $8,761. Not bad. How much should be invested at each rate to get that amount of interest? So, read the problem. Set up a table. Same thing. Invested amount. So, this is your P, principal. Your interest rate, R. Time in years. Notice years. Notice also, like with the distance rate time, we've got P times R times T equals the interest. That table really helps to keep organized. So make the table, start filling things in. Now in this case, you can't quite use the tip that I gave you earlier about using X for the smaller of the two amounts, because you don't know which one is bigger. So just pick one at random. In this case, they picked X for the number of dollars invested at 2.65%. It's going to be left for 6 months or 0.5 years. Notice that the months has to be in years. Don't put 6 and expect to get a right answer. Has to be in years. Imagine that someone's trying to trick you and you have to make sure it's in years. Again, your formula across the top, P times R times T equals I for interest. So X times 2.65%. Now remember that's 0.0265 because you have to change that to a decimal. Multiply those three together, and here's your expression for how much the 2.65% investment gives you at the end of that time. Next. Now this is maybe the trickiest part of this one, because you picked X for one, don't pick Y for the other one, because you do know something already. If you don't know how to do this, remember, the total that the artist got was $410,000. Now, just for fun, let's suppose he invested $200,000 at the first amount. How much would the second one be? Well, if it's a total of $410,000, you just subtract them. So we're going to write that. This is what we would do to solve the problem if these were the numbers. Now, here's the key. This is how we would do it if it were $200,000 for one of them. This is how we'd get it. But we made up this part right here. It's not really that. It's really X. So the other amount is 410,000 minus 200,000, or the real value right now is 410,000 minus X. And that's how you can get this expression when you think you're sunk. You use a simple example, see how you would do that calculation, and then put in the X or Y or whatever you need. Again, the principal times the rate times the time. Notice this is already in years, so you're good. So here's the principal, the rate, and the time. Multiply those together, and that's your interest. So how do we write the equation? Well, the two interests together, we're told, will give us $8,761. So simply add them together. These expressions might look strange to you, but just write them down. That's how much you get from one of the investments. This is how much you get from the second investment, and there is your total equation. Time to solve it. You use that distributive property, and here you go. Simplify, because you need to subtract those X terms, and subtract the 11,931 from both sides. Now notice that the number in front of the X, the coefficient, is negative 0.01585. Divide both sides by negative 0.01585. Negative 0.01585. And there's your answer. Now what does that mean? Well, if you wrote it down, what did X represent? It's how much was invested at 2.65%. So you need two answers, one for the investment at 2.65%, and the second part will be how much at the 2.91%. And notice this answer is a complete statement, a complete sentence. And there's your answer. And then we need to check it. So the 6-month investment, how much do you get? Just multiply the principal times the rate times the time, and that's how much you get from the first investment. For the second investment, we have, this is the principal, this is the rate, and that was 1 year. They left that out. Shame on them. and totals $6,111. Add those together. Oops. Add those together, and there's the 8,761 as we needed. Next, mathematical models are usually equations, sometimes inequalities. You might have something like 5x equals 92, something like that, or you might have something like 52x is less than or equal to 17,920. Could be an inequality. A linear model is a linear equation. And a linear one means your x's only have ones for the exponent, nothing else. No negatives, no fractions, just ones. No twos, no threes. Twos and threes look good, but not for a linear equation. Linear equation has an exponent on the variable of only a 1, also known as just x. So we've got one example. We've got a vented range hood. It takes contaminants like carbon monoxide and so on at the rate of F liters of air per second. The percent of contaminants that are also removed can be modeled by this equation. There's your formula. And we also have a restriction. That rate has to be between 10 and 75. And that's, remember, from up here, it's how many liters of air per second. Now we want to know what flow F must a range hood have to remove 50% of the contaminants from the air. So replace P with 50 because that's what we're ending up with. You want to take a look back there? Got it? 50 is what we're ending up with. Put 50 in the model and solve for F. There's your equation. Put the 50 in and solve. And there's F. So if you want to remove 50% of the contaminants, you have to have a flow rate of approximately 40.40 liters of air per second. Another example, we've got healthcare. That's a big deal. And the expenditures in the United States were Y as in dollars and X as in years. Keep note of that. And it's X is the years after 2000. This is important. We're going to need that piece. So put that in that little box of information you're going to use. Here's the model. Remember, this, years, since 2000. First question is, what were the per capita healthcare expenditures in the year 2018? Well, these are the expenditures, and we're talking about 2018. So what would the X be if we're talking about the year 2018? We're talking about the years after 2000. So X would be 18 years after 2000. So all we need to do is put the 18 in where the X is, do a little bit of calculation, and we can get that answer. Oops, did I make a mistake? No. Somehow they made a mistake though. It should be 18 years because they were talking about 8,000. There's a mistake there somewhere. Okay, let's take a look back here real quickly. Years after 2000. So this must have been the mistake. They meant to put 2010 here. My apologies, but it's not my mistake. I'll see if I can fix that a little bit later for the next time. So there's our linear model. Notice the x has only 1 as its exponent. So they were right eventually. This is an 8. This is an 8 because it's supposed to be after 2010. 2010. So we'll fix that. So just put the 8 in where the x is in the model. There you go. Solve it. There you go. And we've got the answer. The per capita health care expenditures were $11,370 in 2018. Part B. We wanted to know when the expenditures would be 13,000. So the 13,000 will go in for where the y is in the model. There's a 13,000 in for y. X, we don't know. X is going to be the number of years after 2010. We're going to solve that and find out what x represents. So subtract the 8,042 from both sides, divide by the 416, and there you go. So what does that correspond to? Well, we're talking about the year 2010 plus 11.9. So the year 2021. And folks, that's it. I hope you picked up a lot of good tips on this one. If you are ready, go ahead and work some of the problems from 1.2. You can see what the exercises are that I'm suggesting in the syllabus. Bring your questions to class and we'll talk about those questions that you weren't able to take care of. Until then, you take care and we'll see you in 1.3 next time. Bye-bye.